Okay, number 11, Spring 2012, EF 151 final exam. 60-pound package dropped on an uncompressed spring and constant retarding force of 4 pounds. What's the maximum air resistance? What's the maximum distance the spring will compress? Let's sketch out a little picture here. Here's our 60-pound package. Okay, somewhere um, 3 feet above is a spring. Okay. When that's dropped, let's see, where do I want to draw it? It's going to be compressed. Ah, okay. And it will be compressed some distance x, and the package will be sitting on top of it here. Okay. And so we want to determine that distance x, the maximum distance it will be compressed. The other thing we need to recognize is when it's at its maximum distance, the velocity will be 0. And also the velocity is equal to 0 because we drop it. It's at rest when we just drop it. Okay, so hopefully you'll identify this as a conservation of energy equation. We have our two states here, 1 and 2, and we just need to account for all the terms here. Again, don't forget air resistance over this whole distance here. Okay, so we'll see how to factor that in. So let's write out all our terms here. Kinetic energy at state 1, potential gravitational, potential elastic, plus work in is equal to the same at state 2. Elastic 2 plus E loss. Okay, for gravitational we need to find a datum. We've talked about this a lot. The lowest point doesn't have to know where it is, but we know things in relation to that. Okay, so that will make my final potential gravitational energy 0, setting the datum at that point. This distance will be 3 plus x, the initial height here. Okay, kinetic energy, we said both were 0. The initial of the spring, it's uncompressed, so that's going to be 0. We're not adding any energy into the system, so that term's going to be 0. So it looks like we just have gravitational potential energy being converted to spring potential energy and accounting for the losses. Alright, so let's write that out. Gravitational potential energy, CMGH, is equal to 1/2 kx2 squared plus energy loss. That's going to be the loss by air resistance. We know the force, so that's going to be times a distance. Okay, that distance is going to be 3 plus x. To get everything in terms of x, this height is going to be 3 plus x. Okay, so that's the key to the problem, is getting this equation set up correctly right here. mg is the weight of the box, so that's going to be our 60 pounds times 3 plus x. It's going to be 1/2 k, 80 pounds per foot, and x2, or our compression of the spring, is our unknown. Okay, the force is going to be 4 pounds times 3 plus x. Okay, so each one of these terms have pounds in it. Pounds, pounds, pounds. Okay, so the pounds will all work themselves out, and each one of these is going to be, if x is in feet, Okay, each one of these will be pounds times feet. If x is in feet, it's squared here, divided by feet, so that term will be pound feet, and the x in feet here would be in pound feet. So just a quick look at units. I'm going to use the solver to solve this equation. It's going to be a quadratic because we have x squared and x in them. Okay, so math 0. Go up and clear out my equation. Okay, so I'll just take this term to the left and make it negative. So I'll have minus 60 times 3 plus x plus 0.5 times 80 times x squared plus 4 times 3 quantity 3 plus x right there. Okay, I'll guess at 1, and it comes up to be 2.865 or 2.87. And again, the units are feet.